السلام عليكم ورحمة الله وبركاته. How are you, Shabab? How was the major exam yesterday? I hope it was fine. And that was the easiest exams you can have. Okay. Let me briefly go over the exams and all right. Just 4 questions. The first question is an example. In my slides, okay, an example that I solved, everything word by word, okay, everything the same. You know, saying just find the pressure, specific gravity of oil. We use this here, which is now the pressure at B. It's now equal to the pressure due to the height of the oil up plus the pressure due to the air column, which is given by PA. So it is simply PA, which is the pressure due to the air column, the pressure due to the height of the oil, which is gamma oil, and height of oil, which is 1 meter. So from here you find the specific weight of oil, and then what is specific gravity? Specific gravity simply gamma oil over gamma water. Gamma water is already given here, which is constant. So from here you can get specific gravity. Very simple, straightforward. And pressure at C. Pressure at C, simple. Pressure at C would be pressure due to the column, this column of fluid, which is you have water and the height of water. Then plus you have this oil 0.5 oil and the height of the oil, which is 0.5. And the pressure at this point is PB. PB. Simple. Because PB now, which is here, gives the pressure, all the pressure above, all the way. Okay, and PB is already given. So you just add it up to get PC. Simple, straightforward. An example in the class. So nobody should fail this one at all. Should all get 100% in this one. And the second one, which is even here. The solution is even provided here. Okay. Then the second one, this is the what do you call it? The quiz last week. Same thing. I didn't change a word. Just determine the total hydrostatic force acting. And the free body diagram, you have horizontal Fx, but Fx is equal to Fx because it is symmetrical. Okay, the shape is symmetrical. Okay, so Fx will cancel out. So summation Fx equals 0 and is the only one. And then the vertical force, you have Fy acting on this rectangular pressure distribution, and then the weight. So Fy is simply Pa, okay, rho gh, h the height above from here, okay, from the top of the tunnel. Okay? So very simple, straightforward. Okay, find Fy. The weight of the fluid, simply mg, this one, the volume. And the volume here, because it's 3D, okay, it's like 3-dimensional, okay, it goes through. So the volume is going to be the volume of cross-sectional area, which is rectangular, minus this we divide it here, this is 1/4 of a cycle. So the whole radius r squared, it means this area. Then we are removing the area of a quarter cycle, which is this one. Okay, so we are finding this weight now. Okay, times the length L. Okay, so this is the weight in one section, the same weight on the other section. So the total force acting is simply Fy plus 2W, because here you have W and here you have also another W. And simply you add them up. Someone, when I was computer, I will correct this. I forgot. This was the initial one, which was based on what I had before. One of you corrected me in this computation. Everything was correct, only that this is to the power of 8. Okay, and when you change everything again, I uploaded the correct version yesterday. I will change this one also. So when you change everything, this will be 707 meganewton. Simple. So all of you should get this one. All of you. Okay. Someone that was saying this should be a bonus. How will it be a bonus? I mean, there is no error in the calculation. Everything is the same. This is just the computation, which is the power of 8. Simple. So you are not going to memorize this value. But all the steps are correct. Okay, you are not memorizing these values. You are not memorizing them. Okay, you are not memorizing these values. So in the exam, you're supposed to put everything, get your answer. So it cannot be a bonus just because there was a mistake here in the final answer, not in the steps. All the steps are correct. Nothing is wrong with the steps. Okay, only in this power, the power of 5 is supposed to be power of 8. Okay. And then this one, even yesterday I explained it. I took a page, I spent so many minutes explaining this. You have a ship being loaded. This is the weight acting. This is the force acting. It's in equilibrium. So FB equal W. Simple. So here all I need to just write FB equals W and get a points. Here also it is weight has increased, so the buoyant force also has increased, and they are equal because it is still flow. So in this case, FB equal W. That's all I need. Here it is completely submerged because the weight has increased. You can see from the arrow. And the buoyant force also has increased to the maximum point. Here also B equals W. Here the weight has increased that it sank to the bottom. The buoyant force did not increase anymore because this is the maximum value of the buoyant force. So here FB is, that's all I need. All I need for you to get your 20. And the Archimedes WG and extremely empty, the buoyant force acting vertically upward is Archimedes. The buoyant, give me this equation and tell me what is FB, what is, the buoyant. Very simple. Even yesterday in my class, so nobody should fail. This is the last. Which look, this is the location for uniform flow because throughout the full points. One day, this you can see written V function of r and z. Here it says v a function of r. And this radius only, which, so this is where answer is 6. Here the velocity here is increasing, you know, because what? And see, we are not to release the result of the meeting in the 13th week. Okay, so this is till about, okay, that the result is going to be announced. Okay. Not sure the button, sharing button. Stop the sharing and then share it again. So, Euler's equation. This is what we have started discussing. Explain the Newton's second law, Newton's laws, okay? And we have gradient pressure, symmetric pressure, minus is equal to rho A. Okay, so here we're explaining when you have streamline, straight streamline, stagnation streamline approaching a solid object, okay, it slows down. When it slows, the acceleration direction is opposite to the flow direction, and then the pressure gradient increases in the opposite direction, okay, because of this, because this is negative, meaning the pressure gradient is in opposite direction to the acceleration direction. Okay, that is what the negative, because all these are vectors. Okay. This we explain this, the stagnation streamline. Okay. Then explain the second case, that is when the streamline, this is that the pressure gradient is parallel to the streamline. Okay, it's parallel to the streamline. Okay, and increasing to the right. Now, what about if it is perpendicular to the streamline? Okay, if it is perpendicular, then we have to look at the acceleration in the perpendicular sense, which is the AN. Okay, the normal streamline, the normal acceleration, which we say is 0 when the streamline is horizontal, because the radius of curvature is infinity. Okay, explain all this. So here we said because it is 0, so delta P, del P, Z is 0, so it's equal to a constant. Okay, So if it is constant, so this is the same thing as we have in static fluid. Okay, so where the pressure difference here, okay, for stationary fluid, you know, the pressure here at this PB minus PA, okay, is the pressure within the fluid. The same thing here, P is equal to PD minus PC, okay, whether it is stationary or it is moving, okay, it is the same, okay. The hydrostatic pressure remains the same, okay. The hydrostatic pressure, the piezometric pressure remains the same, meaning it is constant, okay. It is constant throughout the field, okay, throughout the field, and that's why sometimes we call it the, okay, we will talk about the static pressure under the Bernoulli equation. We'll talk about the static pressure, which may be somehow applicable to this case because the piezometric pressure may be viewed as the static pressure in a way. Okay, so whether it is static or flowing, piezometric pressure remains constant and the same throughout. Okay, and therefore the variation of pressure with elevation along a streamline and inviscid region is the same as that in stationary fluid. We know, okay, we looked at this also where we have curved streamline. Okay, in this case, when it is curved, when streamlines are curved, the piezometric pressure will increase along a line that is normal to the streamline. Okay, it will increase along a line that is normal to the streamline, and away. Because here you have normal acceleration, it is no longer zero. This is the normal acceleration. Acceleration vector points inwards towards center of curvature. So the normal acceleration here is not zero because you have r. Okay, r is not infinity in this case. So, and normal acceleration is always positive. It is always positive and directed along the center of curvature of the streamline. Okay, and it is always positive, unlike the tangential acceleration, which can be positive and negative depending on whether you have acceleration or deceleration. Okay, so if it is always positive, it means it is always increasing. Okay, always increasing. So this is the direction of the acceleration vector down. Then the pressure field will be opposite. Okay, so it will be increasing away from the streamline, away from the radius of curvature. Okay, so here the direction of increasing pressure is outward. And here we assume that the fluid particle has constant speed because the normal acceleration is when the fluid particle is having a constant speed. And the direction of increasing pressure will be outward from the center of curvature. And this is why the pressure varies. So in this case, when it is along a curved streamline, it is going to vary. It is not going to be constant. Like when the streamlines are horizontal, when the streamlines are parallel, like in steady flow. Okay, if they are straight and parallel, you know, whether static or if it is moving or static, the pressure variation remains the same. The pressure gradient, it remains constant. But here it is increasing. Okay? It is varying because the acceleration, the normal acceleration is not zero. Because the gradient points in the direction of increasing pressure, we conclude that pressure will increase along the line normal to the streamlines. Okay, so pressure will increase along the line normal to the streamlines. Of course, tangent to the streamline depends on whether it is accelerating or decelerating. If the particle is accelerating, pressure is going to decrease in the flow direction. If it is decelerating, pressure is going to decrease along the streamline or tangential to the streamline. This we explained in case 1. Okay. So here pressure decreases towards the center of curvature and the fluid particles experience a corresponding centripetal force, a centripetal acceleration due to this pressure gradient. Okay, because the pressure decreases, so it can easily accelerate. So it is accelerating. Okay, and we call it centripetal force or centripetal acceleration because centripetal means that the force is directed towards a center. Okay, it is directed towards a center. We have the opposite of centripetal, which is centrifugal, which is like pushing it away from the center. Okay, centrifugal force. Okay, so this is called centripetal because it is directed towards the center. Okay, so in this case, if you have curvilinear streamlines, okay, so here the pressure at A is greater than the pressure at B, because this is, if you draw a normal, now this is the direction of the normal acceleration, which is directed towards the center of curvature. So the acceleration increases in this way towards the center of curvature. So the pressure, you consider a particle here, the pressure grade increases in the opposite way. Okay? If it is increasing, then this one is higher than this one is higher than this one. So PA is the highest in this case, while PB is the minimum. Okay? So this is very important. Okay, this is very important. So summary: when streamlines are curved, pressure increases outward from the center of curvature, outward, while the acceleration, the normal acceleration, increases inward. Okay, inward towards the center of curvature in the opposite direction to the pressure. Okay? And each streamline has a center of curvature at each point along the streamline. There is not a single center of curvature of a group of streamlines. Each streamline has its own center of curvature. So don't look at this as if they have the same center of curvature. Each one has its own center of curvature. You don't have a single center of curvature for a group of streamlines. Okay? Of course, when they are straight and parallel, they all have the center of curvature is all infinity. Okay? When they are all parallel, straight and parallel. Now, let's take some few examples to demonstrate the application of Euler's equation in calculation of pressure in a given fluid. Here I want to apply the equation to a column of fluid being accelerated upward. Okay, so you have a column of water in a vertical tube. This is the vertical tube, okay, which is being accelerated by a piston in the vertical direction at 100 meters per second squared, which is the acceleration. Okay? The depth of the water column is 10 centimeter. Okay, and find the gauge pressure on the piston. Water density is 1000. So we want to know the gauge pressure on the piston. That's the water pressure here as it is accelerating. If it is static, the gauge pressure will simply be rho gh due to the height. Okay, if it is static, but because it is accelerating, now we have to incorporate the dynamic component. Okay, the dynamic component, acceleration is going to affect the pressure. Okay, and how will it affect the pressure? We will find the new pressure using the Euler's equation. Okay? And the assumptions here is that the acceleration is constant and viscous effects are not important. Okay, and they are negligible, and the water is incompressible. So here we'll apply the Euler equation in the z direction. That's the direction upward, and integrate between points 1 and 2. Okay? And set the pressure equal to gauge at section 2. This is atmospheric. The pressure here is atmospheric. Hence, it is 0 gauge, isn't it? Because it's atmospheric, so that is 0 gauge. Remember, the atmospheric pressure is the reference pressure for the gauge pressure. Okay? So we now use, since there is no dependence on time, because the acceleration is constant, there is no dependence on time. So the partial derivative in Euler's equation can be replaced by an ordinary derivative. So we use this because we just have one direction, z. Okay. Then we simply integrate. Okay. From cross multiply z, we now integrate. Okay. From point 1 to point 2. Okay. From point 1 to point 2 dz. Okay. When we integrate, this is our piezometric pressure at point 2 minus point 1 is equal to this. Okay. And then when we collect like terms, because at point 2, meaning P2 is 0. Okay, because it's atmospheric. Okay, so now in this case we can bring this pressure here and bring these terms here. Okay, and when we do that, P1 will now be equal to, going to be, we'll still have gamma. Then this Z2 minus Z1 is simply delta Z. Okay, P2 minus Z1 is simply delta Z. Okay, and what you have here is P1 is just simplifying this one. Okay, P1 equals to this. Okay, AZ is given, delta Z is given, so you just substitute and get your pressure, which is gauge above atmospheric. Okay, which is gauge pressure. What about if we say find the absolute pressure? If we say find the absolute pressure, all you need to do is instead of setting this to 0, you will now put the atmospheric pressure here. Use 1.1 or 1.3 kilopascals, the atmospheric pressure. And whatever you are going to find here is going to be absolute pressure in this case. Okay? Or this is one way. Or you set the atmospheric pressure to be 0, find the gauge pressure, and then you add, because P gauge plus atmospheric is equal to the absolute pressure. Okay, so you add the gauge pressure here, 10.9 plus atmospheric pressure to give you absolute pressure. Okay, so this is very simple. We dealt with it in chapter 2. And this is another example in which we'll apply the Euler's equation. Which says we apply it to gasoline in a decelerating tanker. Okay, so like I mentioned here, if you want to find the pressure, if you want to use, if it is static, what will be the pressure? The pressure is going to be rho GH. Rho GH is going to be 9810 times the height, which is what? 10 centimeter meter divided by 100. Okay, this cancel out, so we have everything will be 981 Pascal. Okay. Kilopascal is 0.981 kilopascal. Okay, so this will be the gauge pressure if it is not accelerating, if it is at rest. Okay, and because of the acceleration, you can see that the gauge pressure has increased. Okay, if it were at rest, it's just 0.98, just approximately 1 kilopascal. But because of the acceleration, the pressure has increased. Okay, the pressure has increased. And the pressure at the bottom here is now at 10.9 kilopascal, which is about 11. So like 11 times. Okay, the pressure has increased because of the acceleration. Okay, the pressure has increased because of the acceleration. And that is because acceleration is because of force, because you have force acting. Okay, when a force acts, it causes the particle to accelerate. So how do you find the actual pressure? So the pressure is now, increasing from like 1 kilopascal to 11 kilopascal because of the acceleration. Okay, so this is very important, to understand exactly the application of the Euler's equation. Okay, it helps us to determine pressure as a result of dynamic nature of our system. That's when our system is in motion. In fluid statics, chapter 2, we dealt with chapter 2 or 3? No, chapter 3. Everything that we dealt with was there was nothing in motion. Okay, so when you have movement, how do you now take care of it? You have to go to the kinetics. Okay, although we started with the kinematics. Okay, the kinematics involves studying the motion geometries, in terms of knowing the velocity, acceleration, and space or displacement. And then you have the kinetics. The kinetics now is trying to know exactly what is causing the motion. Because whenever you have motion, you must have force. Force is behind all motion. So in kinematics, we are not considering the force. We are not considering the cause of the motion. We're only analyzing the motion geometries. Okay, the geometry of the motion in terms of velocity field, acceleration field, and the space field. Now, in the kinetics, we are now analyzing, okay, what is exactly the cause of this motion? And the cause of this motion is from Newton's second law, which is force. Okay, so this is the kinematics. Okay, whenever we are talking about the force causing the motion, we are now concerned about the kinetics, okay? The kinetics. That's why in dynamics, you will be drawing what is called kinetic diagram. You have two diagram in dynamics. You have the free body diagram. The free body diagram and the kinetic diagram. Okay, and in the kinetic diagram, all you show is MA usually. That is the resultant force acting on the body and the direction of the resultant force. That constitutes the kinetic diagram. It's taking care of the force that is causing the motion. Okay. Now, this is another example, okay, in which we'll apply the Euler's equation. We'll apply the Euler's equation. It says, the tank on a trailer truck is filled completely with gasoline. This is a tank, a trailer which is carrying oil. Okay, the tank of the trailer is filled completely with gasoline, which has a specific weight of 6.6 kilonewton per meter cubed. The truck is decelerating at a rate of 3.05 meter per second square. So it is decelerating. The tank on the trailer is, so these are the dimensions, the length is 6.1 meter, and if the pressure at the top rear end of the tank is atmospheric, the pressure here, the top rear end is atmospheric, so meaning it is zero gauge. Okay, what is the pressure at the top front? Okay, what is the pressure at the top front? So what is the pressure here? This is the top front. Okay, what is the pressure here? And two, if the tank is 1.83 meter high, what is the maximum pressure in the tank? Okay, what is the maximum pressure in the tank? So here, a decelerating tank of gasoline has pressure equal to 0 gauge at the top rear end. Okay, because it is atmospheric. Okay, and here deceleration we assume is constant, and we have the gasoline which is increasable. And the goal is to find the pressure at the top, the maximum pressure in the tank. So what is the plan? Apply the Euler's equation on the top of the tank. Okay, in the elevation Z is constant, and we evaluate the pressure at the top front, which is this point where we want to find the pressure now. The maximum pressure will be at the front bottom. Okay, the maximum pressure will be at the front bottom. That is this point. Okay, because it is saying we want to find the pressure, and don't forget it is decelerating. So if it is decelerating, what is the direction of the acceleration? The direction of acceleration is in opposite direction now because it is decelerating. Remember that figure where you have a sphere and then you have stagnation streamline, where we're considering particle, okay, which is slowing down. Okay, where we say the direction of acceleration is in the opposite direction. And if this is the direction of acceleration, then the direction of increasing pressure will be in this direction. Okay. Okay. So in this case, you'll have maximum pressure here. Okay. Because this is the last point on the tank. Okay. And of course, it is at the bottom because of the weight of the gasoline. Okay, the weight of the gasoline. Okay, and it is at the end of the tank, because that is the last point on the tank, the last point in this direction, because the pressure gradient increases. It increases this way. The pressure gradient increases this way. Okay, so this is the last point on the tank. So this is where the pressure will be highest. Remember, if it is stationary, what will happen? If it is not moving, no acceleration, okay, pressure at any height is the same. The pressure on the bottom is the same. Okay, at any given elevation, at any given altitude, if it were stationary, but because of the acceleration, the pressure changes, and the Euler's equation now give us the pressure variation as a result of the accelerating nature of the body. Okay, so Here we apply the Euler's equation in one direction, in the L direction, okay, which is simply P over L equal this, okay, and P is the piezometric pressure, okay, and here, integrating, from back to front, we have P2 minus P1, okay, which is change in pressure is equal to minus rho AL delta L, okay. Delta L is just the length. The acceleration is known, okay, and P1 is 0 because it's atmospheric. Okay, so we can find P2. Okay, so this is P2. You see minus cancel. So this is gauge, pound per square inch gauge. Okay, and this in SI unit, kilopascal, 12.5 kilopascal gauge. Okay, so this is P2, but this is at this point. Okay, the pressure at this point is different from the pressure at that point. Okay. Now, what about the pressure at the bottom? Okay, here we also apply the Euler's equation in the vertical direction. So here we use dz, here we use dl. Okay. And here for the vertical direction, in this case, because it is horizontal, you can see the tank is horizontal. Az is equal to 0. Okay, Az is equal to the acceleration. Because it's a straight line, so the normal acceleration is 0. This we explained before, because the radius of curvature is infinity. So the normal acceleration in this case is 0. So the pressure at this point will give us just the pressure of as if the tank was not moving, if the acceleration component is 0. Okay, because if the acceleration component is 0, then this term will disappear, and then you have the piezometric pressure being constant. Okay, and this is the same thing for fluid at rest. Fluid at rest, okay, is the same thing for fluid at rest, that the piezometric pressure is constant. Okay, P2 plus gamma Z2 is equal to P3 plus gamma Z3. Okay, but then this along a vertical line. Okay, along a vertical line. Okay, we know this is P2, this is 0.2, and this is now 0.3. Okay, that's why in this, let me just take you slightly back to correlate. Here we said it is constant, isn't it? It is constant. We mentioned it is constant along the line. Okay, the piezometric pressure is constant along the line, that is delta P. Okay, so to find it, we use the difference in pressure now. Okay, PC and PD. So this will give us delta P. Okay, but along the vertical line. Okay, so that is why here we are not considering this, because it has to be the same vertical point. So we have already analyzed the pressure here. Okay, then so this is like hydrostatic. Okay, so we already know P2, so we just substitute to find P3. Okay, and Z2 minus Z1 is just the height of the truck. So the gauge pressure is now 24.6 kilopascal gauge. In summary, what have we done? The pressure here at this point is 0, which is atmospheric. We now found the pressure here at this point using the Euler's equation. Again, we want to find the maximum pressure. We say it occurs here, because this is the direction of increasing pressure gradient, and then because of the height of the fluid, this is why you'll have the maximum pressure. Okay, because of the contribution due to the height of the gasoline. Okay, and along this straight line, along this face, the pressure gradient is constant. The pressure gradient is constant, and it is 0. So the pressure at this point, the piezometric pressure at this point is equal to the piezometric pressure at this point, which were equated. so as to find the pressure at this point, which is P3. Okay. So this is the simple application of the Euler's equation. Okay. Now let's move to Bernoulli equation now. Okay. Actually, what happened was that Bernoulli did not even state any equation as in equation form. He just made a general statement. Okay, and it was Euler at that point later. Okay, that actually formulated the Bernoulli equation. Okay, and this is because, as we need to see now, that you can get, from the Euler's equation, you can simply get the Bernoulli equation. Okay, but before we dwell into the Bernoulli equation, let's briefly explain some few concepts, okay, that are very important in our discussion. Okay, and one of them is the pressure and flow energy. Okay, what is pressure and what is flow energy? When fluid is flowing, when water is flowing, I mean, what are the energy that definitely anything moving must possess energies? What are the components of this energy that water possesses? Okay, when it is flowing. So, in fact, the pressure. Let me quickly add this. All right. So, what is actually pressure? Pressure. Okay. We know pressure is simply the force per unit area, isn't it? Okay. Pressure is simply force per unit area. And the derived unit, force is in Newton, area is in meter square, isn't it? Okay. Now, uh, pressure is equivalent, the pressure unit Pascal is equivalent to, pressure unit Pascal is equivalent to, which is energy per unit volume, and to the product PV or its equivalent as the unit. Let me. And the product PV and its equivalent. Okay, P over rho has unit joule per kilogram, which is energy per unit mass. What are we trying to say here is this? Okay. When you have this you can Newton per meter, you can introduce meter on top and meter below without changing anything. Okay. When you introduce meter on top, Newton times meter is energy or work. Okay. And meter square times meter is meter cubed, which is volume. Okay, which is volume. So basically, pressure is simply the energy or the potential energy per unit volume. Okay, the potential energy per unit volume. Okay, that is why when you multiply the pressure with volume, okay, when you multiply with volume, it now gives you energy. Okay, it gives you energy per unit mass. Okay, energy per unit mass. Or you can use volume or rho. because if you remember density is mass over volume. Okay? So if we multiply by volume, if we want to remove volume, it's going to be mass over density. So mass, because this is now per unit mass. Okay, so this product PV or P over rho mass of joules per kilogram, which is energy per unit mass. Okay, we'll discuss about why unit mass. Okay, because of intensive and extensive property. Because energy is an extensive property. Okay, which depends on the mass of the system. Okay, so now what we are saying is that when you divide pressure with density, you get this unit, joule per kilogram. Okay, joule per kilogram. Okay, and this is the energy per unit mass, which we call the flow energy. Okay, pressure is a measure of the stored potential energy per unit volume. Note that pressure itself is not a form of energy. Pressure itself is not a form of energy, but it is a measure, meaning it tells us, like it gives us an insight into the amount of stored potential energy per unit volume, okay, in a given fluid. The stored potential energy per unit volume. And that is because, again, like I mentioned, potential energy, as we all know from physics 101, is mgh, and the hydrostatic pressure is rho g h. Okay. Okay, and this is equal to so per unit mass. So energy, if as we say, is mgh over volume. Okay, over volume. Where V now, this is now density. Okay, this is now density. So once we replace density with mass over volume, we have mgh over V, which is simply potential energy per unit volume. Okay, so that is why we are defining it specifically using the potential energy. Okay, the potential energy. And of course, the potential energy is the energy possessed by bodies due to their position in a gravitational potential field. Okay, due to their position, meaning their elevation, altitude in a gravitational field. Okay, we know about gravity, Newton's law of gravity, that the earth has a force with which it attracts all objects towards its center. Okay, so any object on the gravitational field is attracted by the Earth's gravitational field. Okay, so once it is above the Earth's surface, if this is the Earth, any object above the Earth's surface at a distance h above the Earth's surface is possessing potential energy, which is due to the height above the Earth's surface, and the energy is in form of mgh. Okay, and that energy is useful. It can be converted to useful work. It can be converted to kinetic energy, to a lot of other energies. Okay. Now, so this is exactly what I did here. Okay, so this is joule. Okay, joule is simply Newton times meter, which is joule per meter cubed. Okay, this I already explained here at the beginning. Okay, and PV or its equivalent has the unit joules per kilogram. Okay, that's when you multiply with the volume. Okay, so this equivalent, it has the unit joule per kilogram. Joule per kilogram. But don't forget, this is for unit mass. Okay, which is the energy per unit mass, and it is called flow energy. Okay? Flow energy. So ideally here, you have the mass here. Okay, you have the mass here, so you are dividing by the mass. Okay, so that's why we're having it as this value. Okay, check it. So this is called the flow energy or workflow. But what is exactly the flow energy? The pressure force acting, we talked about the pressure force and how to find it, isn't it? So is the pressure force acting on a fluid through a distance produces work. Whenever you have pressure force acting on a fluid through a distance, it produces work. Because work is simply the for a distance moved, force times the distance moved, and it is called flow work in the amount of rho over p per unit mass. Okay, per unit mass. So what are we saying? The flow energy or flow work, simply the pressure divided by the density. Okay, pressure divided by the density. And if you divide this, what you have as the unit? Pressure is Newton per meter square. Density is mass per volume. Okay, so you can see, yeah, mass per volume. You can see this canceling this. Okay, and then you have N over H. Okay, so that's why we say joules per kilogram. Okay, joules per kilogram, which is the flow work or flow energy, P over rho, is in joules per kilogram, which is the energy per unit mass. Okay, is the energy with which the fluid flows, and because it flows because of the flow energy is due to the pressure force acting on a fluid through a distance. Okay, and we discussed about the pressure force in the fluid statics. Okay, discussed so much about the pressure force, its variation in a fluid, and whether it's vertical or horizontal, the rectangular variation, sorry, trapezoidal variation, and the uniform variation. Even in the quiz, okay, the last quiz is about it. Okay, flow work is expressed in terms of fluid properties, and it is convenient to view it as part of the energy of a flowing fluid, and it is called, and we call it flow energy. Okay, flow energy, which is the energy per unit mass, P over rho. Okay. Now, intensive and extensive properties. Any characteristic of a system is called a property. This we explained before, I think, in chapter 2. Some familiar properties are pressure, temperature, volume, and mass, M. The list can be extended to include less familiar ones such as viscosity, thermal conductivity, modulus of elasticity, thermal expansion coefficient, electric resistivity, and even velocity and acceleration. Okay? All these are properties of a system, okay, depending on the system under consideration. And properties are considered to be either intensive or extensive. What is the bottom line? I mean, what do we use in gauging? Okay, intensive properties are those that are independent of the mass of the system. Independent of the mass of the system. When you have water, okay, when you boil water in a cup, the temperature everywhere is 100 degrees Celsius. When you boil it in a tank, as big as, let's say, 10 liters, 10-liter water and 1 liter water, the mass are different because 10 liter has a mass of 10 kg, 1 liter has a mass of 1 kg. As long as they are all boiling, they all have temperature, the same temperature of 100 degrees Celsius. Okay, so it doesn't depend on the mass. Okay, so intensive properties do not depend on the mass of the system. And intensive properties, example of them are, temperature, pressure, and density. Okay, density. So they are independent of the mass of the system. If the density of water, the volume, let's say you have 10 kg water, density is 1,000. If you have 1 million kilogram, the density is still 1,000 kilogram per meter cube. It doesn't change. Okay, the same thing temperature, the same thing the pressure. Okay. Now, The opposite of the intensive properties are the extensive properties, which are those that depend on the size or extent of the system, like the total mass or the total volume. Okay, example, you have total mass, total volume, and total momentum as some examples of extensive properties. Okay? An easy way to determine whether a property is intensive or extensive is to divide the system into two equal parts with an imaginary partition as shown in this figure. Let's say you have these properties: mass, volume, temperature, pressure, and density. So if you divide this into two, will the properties be the same or will they be divided? For mass, mass will be divided, isn't it? Okay, for volume, the volume will be divided into two. The temperature will remain the same. The pressure of the elements will remain the same even if you divide it into two. Okay, the density will remain the same. So these are intensive properties that don't depend on the mass, and these are extensive properties that depend on the mass. Okay, and this is the criterion to differentiate intensive and extensive properties. Any property that you want to examine, whether is it intensive or extensive, try to follow this criteria. Okay, like put it here and then like divide it into two and see, is the property going to be maintained? Let's say momentum. Momentum, is it going to be divided? Yes, it is going to be divided because it is a function of the mass. Okay, larger bodies will possess higher momentum. Okay, because it is a function of mass. So although here it doesn't mean that any property in which the formula has mass will be called an extensive property. For instance, density. Density is mass over volume. It is an intensive property. Okay, it is an intensive property, but mass is as an extensive property. Volume is an extensive property. But density, the ratio of the two extensive properties, give rise to an intensive property, density, which remains the same irrespective of the mass. Okay. Now, each part will have the same value of intensive properties as the original system, but have the value of the extensive properties. And generally, we use uppercase letters, that's capital letters, to denote, just to represent the extensive properties. Okay, except mass. Okay, mass is an exception. You can see V. Okay, all these are in capital letters. And also we use small letters, okay, lowercase letters, to denote intensive properties, with pressure and temperature as the exceptions. Okay, they are the exceptions to this general rule. And extensive properties per unit mass are called specific properties. Okay, extensive properties per unit mass are called specific properties. Let's say we have volume per unit mass. When we divide the volume, we call it specific volume, okay, and we write it in small letter V, okay, specific volume. If it's energy per unit mass, we call it, okay. Some example of specific properties are specific volume, okay, specific total energy, okay, small e, okay, which is the energy, total energy per unit mass, okay, and one of them is the flow energy, which is P over rho that we mentioned. Okay, this is the energy per unit mass also. Okay? Flow energy. Now, pressure and mechanical energy. In the Bernoulli equation, we have to talk about energy because something is moving. And whenever fluid is moving, it possesses energy. In fact, anything in motion possesses energy. Okay, because it means force is being acted upon, because force is causing the movement, causing the acceleration. And whenever force causes a body to perform to move from one point to another through a distance, then energy is present. Okay, so force and distance, you have energy or work. Okay, so now all this we are trying to lay foundation to the Bernoulli equation. But before we talk about the pressure and mechanical energy, let's take a few minutes break and then come back to continue. Okay. We are not yet done. We just went on a few minutes break and we are back. Okay. So someone asking if we are done. I'm sure he just joined. Sure he just joined. Before I had 12 in my class and now I have 13. You should not be joining late. If you join late, I will detect. Okay. And if I detect 5 minutes after the class has started, that will be absent without excuse. Okay. So stop joining late. Now let's continue. Okay. Now we want to talk about mechanical energy. You know what mechanical energy is the form of energy that can be converted um, to mechanical work completely and directly by an ideal mechanical device, okay, such as ideal turbine. Mechanical energy can be converted completely to mechanical work, okay, in motion, isn't it? Moving, something in motion, okay? So it can be completely converted to mechanical work, okay? Like when you have pump, the pump can convert, the mechanical energy or electrical energy to mechanical energy, which would impart on the moving fluid. It will increase the pressure of the fluid, okay, which will set it in motion, okay? And kinetic and potential energies are the familiar forms of mechanical energy. Okay, we know the kinetic energy is the energy possessed for all moving bodies, and the potential energy is the energy possessed due to position in gravitational fields. Okay, it is maximum if it doesn't depend on it depends on position only. It doesn't depend on velocity. Okay, but kinetic energy is half mv squared. So you must have velocity. For velocity equals 0, it means AE, as we know, is half mv squared. So it depends on velocity. The higher the velocity, the higher the kinetic energy possessed by the body. Okay, and if velocity is 0, then it means Ke equals 0. And the potential energy doesn't depend on velocity. It depends on the height above the gravitational field. Okay, so it can be present whether the body is in motion or it is static. Okay, whether in motion or static, you still have potential energy. Okay, but still for something, when an object is static, then you have only potential energy. Okay? But when it is moving, you have both potential energy and kinetic energy. Okay? We will elaborate that in the few slides coming. So pressure, as we explained before, is a measure of the stored potential energy per unit volume. And not that pressure itself is not a form of energy. This we explain. Pressure as it is not a form of energy. Okay? It is a measure of the stored potential energy per unit volume. I think, okay. Okay, I will check this slide too, because it has repeated some things we did before, so I will check and edit it. Okay, so this we did, the flow energy again, which is as a result of the pressure force, okay, acting on a fluid through a distance, produces work called flow work. Okay? The flow energy is this a unit mass, P over rho. Okay, so this we explained before. So here we're explaining components of mechanical energy that affect fluid flow. Okay, one, you have the kinetic energy, which is because of the motion, the velocity possessed by the fluid, half mv squared. Okay, and then we have the potential energy, which is the energy possessed by the fluid as a result of its position in the gravitational field, and then we have the flow energy. Okay, flow energy per unit mass. This per unit mass. If you want to express the kinetic energy per unit mass, it's just going to be E squared over 2. without m, isn't it? This per unit mass. If you want to express the potential energy in per unit mass, it's just going to be GH or GZ. Okay, where Z is the vertical distance of the gravitational field about the Earth's surface. Okay, GH or GZ. Okay, removing the m. Okay, if it is per unit mass. Okay, like this one, this is per unit mass. Yeah, so so now we have three energies, okay, three parts of the mechanical energy, which is the energy that is converted to mechanical work, okay? Fluid are doing work, okay? And they're doing work when you look at turbines, okay? Turbines where you have tide, water falling onto a tube, turn it, and then produce electricity, okay? Okay, so fluid possess mechanical energy, and that energy is in form of kinetic energy, potential energy, and flow energy. Okay, and flow energy. Okay, and flow energy. So now, the mechanical energy of a flowing fluid can be expressed on a unit mass basis, that is per unit mass. Okay, using this. So this is now the mechanical energy of a flowing fluid. Okay, on a unit mass basis. Okay. So this is the energy per unit mass of a flowing fluid. Okay, this is the flow energy. Okay, this is the kinetic energy. This is the potential energy. All of them per unit mass. If we want to have our mass, we'll just introduce m here, and m here. It's not per unit mass. Okay, and that is, we all know that energy is an excessive property because it depends on the mass. Okay, energy depends on the mass. You can see all of them, they all depend on the mass. So this is now the total energy, okay, for a flowing fluid, the total mechanical energy. Now, what is the Bernoulli equation? The Bernoulli equation is simply saying that the mechanical energy is conserved, meaning the total energy of a flowing fluid remains the same along a streamline. That is the simple way to explain the Bernoulli's equation. The sum of the flow energy, kinetic energy, and the potential energy on unit mass basis is the same at every point along a streamline. This is it. Meaning, when you have a streamline, when you consider point 1, point 2, this energy per unit mass, E1 here, E2 here, so it's telling you E1 is equal to E2. Simple. Okay, meaning it is, this expression is constant. C is a constant. If it is constant, then E1 equals E2 equals E3 equals E4. It is conserved. It is more or less like a statement of the conservation of energy. That's why I explained the mechanical energy. So it's more or less like saying that the mechanical energy of a flowing fluid is conserved, but there are conditions. The flow has to be incompressible, and then it has to be steady. For incompressible and steady flow. Okay, we are going to explain about the limitations of the Bernoulli's equation. But here I like summarize it. This is like the summary of the Bernoulli's equation, that the mechanical energy of a flowing fluid along a streamline, if you consider a given streamline, is conserved, is the same. And energy conservation is saying that energy is neither created nor destroyed, but can be transferred from one form to another. So as the fluid is flowing, there is transfer of energy. Kinetic energy and the potential energy are changing to the flow energy. And the flow energy, which is basically to do with the pressure. So the kinetic energy and the potential energy can now make the pressure to increase, can change in such that the pressure of the flowing fluid can increase. And this is because the interchange of energy between potential, kinetic, and the flow energy. Flow energy is a function of what is called the static pressure, which is P. P is the static pressure. Okay, P is the static pressure. Okay. Now let's move to the okay. So this is the simple derivation of the Bernoulli equation. Okay. The simple derivation of the Bernoulli equation is from the Euler's equation. This is the Euler's equation. All we are saying is that we select a particle on a streamline. Yeah, this is the streamline that is moving in your curvilinear path. Okay, and the position S. Okay, the position coordinate S gives the particle's position, and the unit vector ut is tangent to the streamline. So here it will have velocity along this tangential velocity along the streamline, and this is the normal, component, the unit vector. Okay, the unit vector directed towards the center of curvature for the normal velocity. Okay. So assume steady flow so that the velocity of the particle depends on position only. For steady flow, it depends on position only. It doesn't depend on time. Okay. And assume that viscous forces on the particle can be neglected. This is another one of the assumptions for the Bernoulli's equation, that viscous forces on the particle can be neglected, most especially closer to the, any solid boundary. Okay. So if viscous forces can be neglected, then if we apply the Euler's equation, yeah, so this is the acceleration, okay? You know this, okay? So for steady flow, del V del T is 0 because velocity is constant with time, okay? And if the velocity is constant with time, so here we have V del S, okay? So this is the acceleration, which is the tangential acceleration in this case, okay? It is the tangential acceleration. Now, because the pressure, the elevation, and velocity in these equations depend only on position. Yes, the partial derivatives becomes ordinary differential, so we change from del to d. Okay, okay, we just change from del to d. Okay, and then so this is rho v dv ds. Okay, and the v can go inside. The v can go inside the differential, become v squared, but over 2. Why over 2? Let me quickly differentiate this. Because when we differentiate v squared, what we have? We have 2v and then dv ds. So to take care of these two, so that's why we are dividing by 2. So that when we differentiate dv squared over 2, we will have 2v over 2 dv ds. So you see these two will cancel out, and then at the end we will have v dv ds. So we are going back to where we started, which is this one, v dv ds. Okay, so that is why we are introducing these two here. Okay, and when we do that, you can see d by ds, d by ds. Okay, so we can take it out, and when we factorize it, we have this. Okay, and this is equal to 0. Okay, this is equal to 0. Okay, and then now when the derivative of an expression is 0, when the derivative is 0, then it means that the expression is equal to a constant. Okay, it means that the expression is equal to a constant. When the derivative is 0, it means that the expression is equal to a constant. When you cross multiply, ds times 0 is 0, so you have d of this. When you integrate, it is simply saying integral of dp plus gamma z plus rho v squared over 2 is equal to integral of 0. Integral of 0 is constant. You get c. Integral of d of this, you get the same value here, which is p plus gamma z plus rho v squared over 2, okay, which is equal to a constant, okay? So that is why here it's just the integral of, when the derivative of an expression is 0, the expression is equal to a constant, okay? So now e plus gamma z plus rho v squared over 2 equals a constant. And if it is equal to a constant, then it means P1, gamma 1, Z1, this 1 is equal to P2, like that, okay? Because it's equal to a constant value. It doesn't matter the point, okay? So here, this is the expression of the Bernoulli equation, and it is called the pressure form. This is the pressure form of the Bernoulli equation, which has all the terms. We have the units of pressure, okay? This is the static pressure, okay? This, we call it the static pressure. This, we call it the dynamic pressure. This is static pressure, okay? And this, we call it the dynamic pressure. And this, we call it the hydrostatic pressure, which is due to the elevation. It's not actually a pressure per se, but it's because this Z is different from H, okay, pressure head, okay? Because this Z, this pressure in this case, it decreases with depth when you go decreasing because the elevation is decreasing. It is simply the potential energy, okay, which goes down when Z is decreasing. But hydrostatic pressure, when you go down, it is increasing within fluid, okay? But it is still referred to as hydrostatic pressure. But this is the explanation. You have, P is the static pressure, dynamic pressure, and then this is the hydrostatic pressure, and this is the pressure form. The Bernoulli equation has many forms. In the previous slide, I just introduced you to the energy form of the Bernoulli equation. This is the energy form of the Bernoulli equation, where you have P over rho plus V squared over 2G plus GZ, okay? And these two are equivalent. This is equivalent to this one, okay? The other one, the pressure form, sorry, the energy form is saying P over rho P over rho plus V squared over 2 plus GZ is equal to a constant. Okay. And this is the energy form, okay, which is per unit mass. And here, this we call it the flow work, the flow energy, which is as a result of the static pressure, okay, as a result of the static pressure or the hydro or the pressure force acting, okay. And then the second one, we call it the kinetic energy, okay, which is as a result of the dynamic pressure, okay. It is constituting the dynamic pressure, okay. The dynamic pressure is corresponding to the kinetic energy, and this is the potential energy, which is corresponding to the hydrostatic energy in this case, okay. So this is the energy form of the Bernoulli equation, and this is the pressure form, this is the pressure form of the Bernoulli equation. Okay? Here, each term is in energy per unit mass. Here, each term is in pressure, okay. The Bernoulli equation has many forms. But you need to understand that when you combine them all, I mean, they are just one and the same thing. Okay, they are just being expressed because it depends on the area. You know, we will even go to the last one, which is the head form of the Bernoulli equation. Okay, the head form. Now, dividing this by the specific yield, like here, by the specific weight. Okay, if we divide by the specific weight, we will have the head form of the Bernoulli equation. If we divide the pressure form by the specific weight, which is gamma, we'll have P over gamma plus Z plus V squared over 2G equal still a constant. Because when you divide a constant by another constant, you will still end up with another constant. Okay, so this is the head form. Okay, this is the pressure form of the Bernoulli equation. This is the energy form, and this is the head form in terms of head. Okay, because this is the pressure head now. Okay, we call this the pressure head, and we call this the elevation head. Okay, and we call this now the velocity head. Okay, so the velocity head is corresponding to the kinetic energy, is a measure of the kinetic energy of the fluid, okay? While the elevation head is a measure of the potential energy of the fluid. And the pressure head is a measure of the flow energy of the fluid, okay? It's a measure of the flow energy, okay? This we will also demonstrate you using the heads, I mean, using some pictorial figures, okay? So these are the three forms of the Bernoulli equation, very important to understand, very important. This is the energy, the pressure form, the head form, and this is the energy form, okay, of the Bernoulli equation. And that's why it's very important for civil engineers, for mechanical engineers, and for chemical engineers, okay? Now, Bernoulli's equation simply says, you know, in terms of energy, that the sum of the kinetic, potential, and flow energies of a fluid is constant along a streamline during steady flow when compressibility and frictional effects are negligible. Frictional effects, that is viscous effects, okay? Viscous forces when they are negligible, okay? And they become negligible, you know, far away from the boundary. We are going to expatiate more on that. So here you have the energy form. Okay, this is the flow energy, kinetic energy, and the potential energy. And then this is the head form. Okay, this is the pressure head, velocity head, and the elevation head. And this is total head, which is constant. Okay, and the Bernoulli equation can be viewed as the conservation of mechanical energy principle, like I mentioned before, because this is all we are saying here using the energy is that the mechanical energy of flowing fluid is conserved. By conserved meaning it remains constant, it remains the same, okay? And the sum of the pressure, velocity, and elevation heads along a streamline is constant during steady flow when the compressibility and frictional effects are negligible. This is the statement of the equation in terms of the head. This statement in terms of the energy, okay? And you can make another statement in terms of the pressure, okay? That the static pressure, okay, the static, dynamic, you know, and hydrostatic pressure remains constant along a streamline, okay? Now, talking about energy. When a body is raised above the ground, above the earth's surface by a height, deltas, by a height, okay? You can see this is a rock. At this point, it is static. So velocity here equals 0 at this point. It possesses kinetic energy, PE1, 10 kilojoule. Kinetic energy is 0 because there is no velocity. It is not in motion. Okay, it is not in motion. Kinetic energy is a function of velocity. If the velocity is 0, no kinetic energy. But when you throw it down, okay, it begins to accelerate. A constant value, g equal 9.81, isn't it? So once it accelerates, the velocity increases, isn't it? So when the velocity is increasing, the kinetic energy will be increasing because the kinetic energy is simply half mv squared. So when the velocity is increasing, the kinetic energy is increasing. What happens to the potential energy? Z is reducing because this is mgz. This is the kinetic energy. Z is going down. So if the value of Z reduces because m is constant, G is constant, but G is reducing. When G reduces, the potential energy reduces. So kinetic energy increases and potential energy decreases. So there is conversion of energy. The energy is converted from potential energy to kinetic energy. And that's why at some point here, you see the kinetic energy has increased from 0 to 3 kilojoule. The potential energy has dropped from 10 to 7 because it has lost this distance, delta z. It has lost value, mg delta z. This is the value lost because of the reduction in height, okay, as it goes down. So that's why we say if this is fluid, when you go down, the pressure increases. So that is why this term, the potential energy or the elevation head, which we call the hydrostatic energy, using the hydrostatic energy, the hydrostatic pressure in the pressure form, okay, it's not actually pressure because it is opposite to how pressure behaves. Pressure, when you go down the fluid, the pressure increases. But for the hydrostatic, for this one, okay, the elevation pressure, let's call it the elevation, the potential energy, when you go down, the potential energy the elevation or the potential energy reduces, or in that case, the hydrostatic energy, okay, it reduces, okay? So it's not actually pressure, okay? And when it comes to the ground surface at this point, okay, kinetic energy now becomes zero, because velocity, it will come to rest, and the potential energy also zero, because Z is zero. And what happens to the 10 kilojoules that it has? It has been converted to thermal energy, to sound energy. You know, when a rock hits ground, so it will, that energy it has, which is 10 kilojoules, has been transferred, has been converted to another form, thermal energy. Okay, the temperature, I mean, the thermal energy, sometimes light energy, because it may create light as a result of the impact. Okay, but the kinetic becomes zero and the potential energy becomes zero. So when fluid is flowing along either in open channel or pipe, these energies, potential, kinetic, they keep changing. Okay, they keep changing sometimes, to increase the flow energy, okay, or the pressure head, or sometimes the flow energy may change into the kinetic energy. Okay, into the kinetic energy because of the velocity. Okay, it can be converted. So there is transfer of a conversion of energy from one form to the other as the fluid is flowing. Okay, but when you sum them up, when you add all the energies, mechanical energy, flow energy, kinetic potential, it remains the same. Okay, it gives you, when you add them up, they give you the same value. Okay, and this is the definition of the Bernoulli equation. Okay, which is simply like if you consider 2 points or 3 points, so this is point 1, point 2 along a streamline. Along a streamline, this is point 3. It remains the same. Okay, it remains the same. Applied along streamlines, and then velocity and pressure varies inversely. Why? We are going to explain that. Because if you look at this, okay, if you look at this, if it remains constant, so this is piezometric pressure, isn't it? This piezometric pressure. There's simply piezometric pressure plus the velocity head. Okay, the piezometric pressure plus the velocity head, or the dynamic pressure. Okay, so if it is a constant, then it will be varying. If this goes up, this will go down to maintain a constant value. If the piezometric pressure increases, then the velocity has to decrease. Okay, and that simply means that in a flow, when the velocity increases, then the pressure has to drop. Okay, the pressure has to drop. The piezometric pressure has to reduce. And when the piezometric pressure increases, then the velocity has to reduce. And this we are going to do it practically in water engineering, CE 335. Okay, when simulating flows in fluids. Okay, we are going to see exactly to measure the velocity using pitot tube, which is the next part that we are going to explain. Okay, we will see this variation of velocity with pressure. When the velocity increases, the pressure has to drop. Okay, and when the increases, the velocity has to drop. Okay, and physical interpretation of the Bernoulli equation, we explain that energy is conserved. Okay, and one way to interpret is leads to the idea that when Bernoulli equation applies, the total head of the flowing fluid is constant along a streamline. Okay, so here we are using the head form of the Bernoulli equation. Okay, this is the pressure head, elevation head, and the velocity head. Okay? The total head remains constant. Remember that this is the piezometric head, okay, which we did before. And then, so the piezometric head plus the velocity head remains constant, okay, along a streamline. So when you combine them, piezometric head plus velocity head, it remains constant along a streamline. Okay. So this is the pressure head, this is the elevation head, and this is the velocity head. And this is the piezometric head when you add them up. Okay. So head is a concept that is used to characterize the balance of work and energy in a flowing fluid. Okay. And head can be visualized as the height of a column of liquid. Okay. Can be visualized, and each type of head describes a work or energy term. Okay. Each type of head, okay, describes work or energy term. This we explain, okay? The pressure head describes the flow energy, okay? The elevation head describes the potential energy, and the velocity head describes the kinetic energy. The velocity head characterizes kinetic energy, elevation head characterizes gravitational potential energy, the pressure head characterizes the pressure force and characterizes the work done by pressure force and characterizes flow energy of a flowing fluid. And the total head is constant if we neglect the viscous effects. Okay, and this means that when the Bernoulli equation applies, the fluid is not losing energy as it flows because the energy is constant. The mechanical energy is constant because the viscous effects are the cause of energy losses. Viscous effects are negligible when Bernoulli equation applies. Okay, viscous effects are the cause of energy losses. Okay, so we will continue from here in the next class. If you have any question, please go ahead. All right. So see you next week. Next week we are going to have a quiz. Okay? I will check the section that is going to apply. Okay. But next week we are going to have a quiz. Quiz will just apply to. Okay. I will let you know.